Okay, Don, I'm going to focus the camera so we can see the sunspot better.
Okay, go ahead.
They've built up a picture of how the magnetism behaves around sunspots.
The magnetic field coming out of that sunspot is almost like a fountain. It comes up out of the center, very concentrated, and spreads out. And usually sunspots come in pairs or maybe more. And the magnetic field will come out of one sunspot, maybe North Pole, like on a magnet, and go into the other sunspot that would be South Pole.
The sun's plasma traces out the magnetic field lines between North and South poles. When the sun becomes more active, the magnetism is more complex. Then, the surface is turned into a carpet of magnetic turmoil. That's what causes even more sunspots to break out. The sunspots look dark because they're cooler than the rest of the sun. Spots form where the magnetism is strongest. The invisible force field diverts the rising heat away from those parts of the surface and makes them cooler.
If you could stand in the center of a sunspot, you would see that it is slightly depressed. It looks sort of like a dish shape.
The sun's magnetic field lines stretch way out into space. Sometimes they are traced out by its hot gases and form massive loops. These are prominences. The lines of force act like invisible threads, drawing the plasma out. It can hang above the sun for weeks.
If you could stand near a prominence, you would see thousands of miles, perhaps, a loop that large with material flowing along the magnetic field. You don't see the magnetic field, you see the bright material.
Loops of gas that could stretch from Earth to Moon.
Magnetic field lines, when they form a prominence, are following a shape just like you'd see around a bar magnet. It's the same pattern. Often they start as small loops and they build up, and over a period of time they may disconnect, and material then actually flows out into space.
A massive solar slingshot hurls out millions of tons of particles. It may seem to be going slow, but this plasma is traveling so fast, it would cross the United States in less than a minute. Shock waves from a sudden, violent release of energy. Like a pressure cooker blowing off, it releases some of the sun's pent-up fury. For a few seconds, a single flare throws out as much energy as the whole of the sun. For a short while, a flare can be the hottest place on the sun, hotter even than the core.
A flare is activity, like a prominence or a sunspot, but in this case, the activity is very strong and short-lived, and it's a brightening. A very rapid brightening over a period of minutes in which material is actually thrown out into space. The strong solar flares are actually quite dangerous because the flare throws out so much material in a short amount of time. We have disruption of radio signals, we have satellites that may go out of operation. We actually need to know when a flare goes off in order to prepare for it.
Solar terrestrial indices for 28 October follow. solar flux 108 and Boulder A index 10. Repeat, solar flux 108.
Boulder, Colorado. This is the National Space Weather Center.
In the NOAA Space Weather Operations Center, we monitor the sun 24 hours a day, 7 days a week.
The Boulder K index at 0-100 hours UT on 29 October was 3. Repeat, 3.
Today, Courtney Williamson is the center's weathercaster. Others plot and map the sun's activity.
The magnetic field was quiet to unsettled.
One of the things we worry about is solar flare activity.
Solar activity will be low.
Now, these bright areas are areas of very strong magnetic fields, and sometimes these magnetic fields become very contorted. When they do so, they want to release their energy, and they do that in the form of a solar flare.
8 minutes after a flare, the Earth is blasted with X-rays and ultraviolet, playing havoc with communications. 1984. All communication between Air Force One and ground control has been blacked out. By the time President and Mrs. Reagan deplaned in China, the U.S. military commander-in-chief has been out of touch for several hours. There was nothing anyone could do about it. Even satellite communication was affected. In a solar storm, rays of energy fry Earth's upper atmosphere. The thin air expands, dragging down satellites that would normally orbit high above. But flares aren't the only result. Prominences may show up as bright loops on the rim of the sun. But when seen head-on, they appear as thin black streaks. And they take on a different name: filaments.
They sit higher in the solar atmosphere, and sometimes they erupt from the sun. When they erupt, they make their way into the solar wind and propagate towards Earth.
The solar wind is a stream of charged particles coming out from the sun. Our star constantly blows itself away, sending 1 million tons of electrons and protons into space every second. Our first clue to the existence of this wind came decades ago, from comets. 1986, Comet Halley. Touched by the sun's warmth, its ice and dust boil off. 10 years later, Comet Hale-Bopp, seen with 2 tails. One, a yellow trail of dust and dirt that litters the comet's path. The other tail, electric blue, its glowing gas, charged particles, and like a windsock, it blows in the direction of the solar wind. This tail always points away from the sun, but there are better ways than comets to see the solar wind in space. Satellites feed the screens at the National Space Weather Center.
This is solar wind density, velocity, and magnetic field.
They show Joe Kunches exactly how the solar wind is blowing.
Right now, the velocity is around 1 million miles per hour. If it were twice that, we would be in a condition that we know is related to strong geomagnetic storm activity on Earth.
SOHO can see the storm on the horizon. With a disk in the center to blot out the sun's glare, it sees the particles that are blasted out from the sun. They strike the camera's sensor and sparkle. Blast after blast of electric particles will pummel Earth's magnetic field. It takes a pounding, sometimes with devastating consequences for our planet. This computer image shows the Earth's magnetic field being blasted in 1997 by massive gusts of wind. The normally calm field, shown here in gray, rocks violently as waves of particles strike it. Blasts like these can knock out power grids. The wildly changing magnetic field acts like a dynamo, generating extra electricity in cables. Circuits trip or blow. Quebec, 1989.
This morning, 6 million people across Quebec woke up to darkness and disbelief. People at Hydro-Quebec are not positive, but they think the blackout was caused by the sun.
Darkness for Montreal, but lights for the rest of America. The particles that knocked out Quebec made it down to Earth and set off the aurorae, the northern and southern lights. And it glows. Although the NOAA Space Ops Center has the most sophisticated solar storm warning gear, they still need the human eye to see the subtle changes. Larry Coombs watches the activity build up and knows we're heading for a big one.
We can expect a lot more features on the sun than we have even today. We can expect, along with those features, to have more disturbances coming from the sun toward the Earth.
Solar activity waxes and wanes. Every 11 years or so, its magnetic field twists itself like an elastic band before it snaps over. 1985. It's quiet with large gray areas of neutral magnetic field, the start of a solar cycle. 5 years later, the activity has increased. The spots are the poles of many magnets. By 1991, at the maximum, it's a riot of magnetic disturbance. Then, the magnetism calms down and the solar features fade away. 5 years later, it's back to calm and the cycle goes round again. The next solar maximum is due soon, and the Space Weather Center takes advantage of the calm before the storm.
Terrestrial conditions for the last 24 hours follow. Solar activity will be low. The geomagnetic field will be quiet to unsettled.
These city lights were once sunlight. Plants and animals soaked up the solar energy before they were turned into fossil fuels. The glint of billions of stars. Millions of nuclear engines sparkling in the night sky. Even the moonlight bathing the tree is starlight. We only see the moon because of the sun's rays that bounce off it. But storing that energy as coal and oil has taken millions of years. Is there a faster way to gather it? The amount of energy that comes from the sun is phenomenal. If we could somehow gather all the energy that fell on the Earth in one day and store it, it would supply the energy needs of the whole world for 30 years. If only we could reap that energy. Barstow, California. When it comes to solar farming, Dave Ribb knows you've got to think big.
Well, we're in the world's largest solar power facility.
Dave's got 11 million square feet of reflectors.
We make enough power here on the average for about 50,000 homes.
In his giant California field, although he grows no crops, he still manages to have a harvest.
We're collecting the sun's energy by concentrating it with these parabolic-shaped reflectors onto a central tube where we have a fluid that heats up and then carries that energy in the form of heat to heat exchangers where it makes steam.
The fluid inside the tube is oil, frying in the heat of the sun. Hotter than molten lead, each square yard of reflector gathers enough power to run 5 TV sets. From sunlight to electric lights. But even though he's choreographed 500,000 reflectors to track the sun across the sky, some sunbeams still escape Dave.
We count on about 30 cloudy days per year and more days that are partially cloudy, but that still leaves a vast majority of clear, sunny days.
Solar power will never provide all our electricity. But why try to collect the energy from a star 93 million miles away? Some people want one a little closer. General Atomics, San Diego. Welcome to the Star Factory. This is where they dare to fuse atoms.